the first thing is that you have to find that the impedance of what's the value for the impedance, what's the value for the resistance of this transistor. So the resistance of the transistor is 31.25. First step is to normalize that. And we know that the transmission line, assume that our transmission line is 50 ohm. So we normalize that to 50 ohm. So we find that, and then I said that we are interested in admittance. So this Y at point A equals to the 1 over R divided by Z, which is equals to 1.6. What's the unit for this? 1.6 watt. Okay. Yes. Yeah. Okay. So where is the point 1.6 of admittance? Where is the point 1.6 on admittance? Did you find that? So when you look at these values here, so the red values show the value of the resistance, and the blue values shows the value of the conductance. Okay, and you know that this line is the pure resistive or conductive. Okay, so the value for A is exactly at the 1.6, which is here. Here is, and then the next step is to add this capacitor, CL, and then this CL again in the admittance you have to find the value for the susceptance of this capacitor, which is coming from this formula. Actually it's coming from this formula, 1 over J over susceptance is coming from 1 over J over C, J omega C, and the value is this. So now we have to move 1.2 from this point, from point A in the positive susceptance. What is the positive susceptance? I should go up or down? Down. So what is the value for 1.2? So the value for 1.2, which is mentioned on this graph, here it is mentioned here. Here is 1.2. So this is the 1.2 circle. Okay, and then we have to move to the intersection of these two, which is here. So this is point B. Point B is admittance, conductance. Yes, it's conductance. It's J. It's G. Blue value. It is conductance. Yeah. Is it 1 point? Yeah, true. its blue value. I didn't get, yeah, it's 1.6. 1.6 or 1. I thought maybe this one is 1.8 and this one is 1.6. Is it clear, guys? I just moved to this point, which is 1.6 plus J1. Point B is there, all right? Now I have to look at the impedance of this because I want to make this circuit in series with one inductor, okay? So what's the value for impedance of this? Just look at this point and read the red line. So one red line is coming from this point 3, and then this also is coming from point 4. So it's point 4 minus J point 3, which is, we have easy. All right. Now I'm going to add this amount of reactance to my circuit, okay, which comes from the value of the L, which is 1.1. So how did I find this? You have this value for the L, 4.4 nanohenry, and then you know that what's the value for the omega, which is getting here from S. So you find this value of, always consider and don't forget to normalize, because if you don't normalize this, you get a, I don't know, 56. So it's 55, so it's wrong, all right? So always normalize it. So we are working on normalizing. And then you add this 1.1 to the previous that we have 0.4 minus J.3 added by 1.1, you are going to 0.4 plus J.8. So we are moving to 0.4, intersection of the 0.4, which is the red 0.4, it's impedance. So this is the red 0.4, and this is the 0.8. This is 0.8. We are here. Again, I'm looking at the admittance of this, which is very easy. It is intersection of this circle and this circle. So this circle is coming from this number. This circle is coming from this number. If I do not make a mistake, or this number. Yeah. 0.5 and 1. So this is 1. So this is minus J1, and this circle is 1. Okay.
Can you repeat point C again?
Loud.
Can you repeat point C again?
C. So for C, so you understand that we have to go to this point. So just look at what is the value, I mean, what is the location for this 0.4 plus J 0.8 on the admittance. So 0.4. So 0.4 is this circle. You see that this is 0.4. Okay. This is 0.4. So this circle is 0.4. Sorry, it's an impedance. It's an impedance. So this is 0.4. This is 0.4. Okay. And also 0.8. So 0.8. 0.8. Yes, 0.8. You have to look at it. So this is 0.8. So this line. So the intersection of these two lines is this point. YC, you should read YC. So YC is the intersection of this line and this line. This is 0.5 and 1. Okay. And now I'm going to add, so this is C. And then I'm adding another capacitor. Again, you calculate the normalized value of this capacitor, which is 1.5. I add this 1.5 to this number and we reach this point. 0.5, J.5 on admittance. So 0.5 plus J.5. So it is somewhere in the lower half. So 0.5 is again this circle, and J.5 is this circle. This is J.5 and this is 0.5. So this is the point E. And then we read the value for the impedance. The value for the impedance is the intersection of this circle. This is circle 1 and this circle. And this is also circle J1. So this is minus J1. This is R1. And then you add the value of 1 and you see that the final value equals to 1. And then we denormalize it and we see it's 50. So by adding some capacitors and inductors, we change the input impedance of the transistor to 50 ohm. Why we are interested only with capacitors and inductors? Why didn't I add a resistor? I can add a resistor and then just move from, I add a resistor and then move on this line and reach this point. Because resistors consumes our power. Never use resistor in this machine.
So why you find?
Because now I want to come out of this Smith chart and say that what's the Z in. So the Z in is the value that you see here multiplied by the characteristic impedance of the transmission. Because in the first step you normalize everything. In each step actually you normalize. So you normalize your values and insert it into a Smith chart and play around them. So the final step, when you read the value, again you have to. Yes. Again, for example, a transmission line, you normalize it and say that the transmission line is just a phase shift. Just changes the phase. So normalize and then go inside. So it is a phase shift. Right. Yep. 20. Yes. You mean that instead of this circuit we have this circuit. So everything is then set. So not here, you don't need to change anything. Z, another Z, another Z. Capacitance in series gives you susceptance, yes.
then add, then again
Why
find
it's
the
not
corresponding susceptance, and then add the susceptance to the capacitance, and then find the corresponding reactance.
no. So capacitance gives you in series again gives you reactance. It does not give you susceptance. It gives you a reactance, but it's a negative reactance. I mean the value that I don't know why it's. On the Smith chart, you are looking at the impedance and admittance, and then you calculate the values for the impedance or admittance of the component that you have. If it is in series, then you have to look at the impedance. Impedance of a capacitance is just a reactance, pure reactance. But it's a negative reactance. It's a negative reactance. Okay, guys, we are going to networks, but we mentioned at the beginning. So the networks, guys, okay, leave it for after the class. So the networks. It is very useful that we are looking into a circuit, I mean a complex circuit, without understanding what's going on inside. Because then we have lots of components. For example, we have an op amp, tens of transistors, lots of parasitics inside it. But when we are looking at a black box, by just looking into the ports that we define for that black box, and then we characterize that black box, it's very useful, especially in RF, because it's not important what's going on inside this network. If I know that what is the voltage, input voltage and current of this network, then I can simply connect this network to the rest of my circuit and then use it and characterize it and analyze my circuit. So it's very important to divide complex networks into sub-networks and then analyze each of them, find the parameters of those networks and then play with the network parameters. This is the idea. So most of the time we are interested in the overall circuit performance instead of the individual components. So we define one port network when it has only one port, two-port network when it has two, and then multi-port network has one. All right? In electrical and electronics, so the things that we are mainly interested, especially in low frequency, is the current and voltage. Anything in the electronic defines based on voltage and current. So, and then we say that a port of a network has two variables, I and V, and then we characterize the specification of this network based on these two parameters. We have four different types of parameters. We can say that a network can characterize based on the Z parameters or Z matrix. And this Z matrix coming from here. If I say that the voltage at the port I, or at the port, for example, two-port network at port 1, what is the relation between the voltage at port 1 with the current at port 1 and current? then I define two parameters, Z11 and Z12, and these two parameters is the characteristic of my network. And again for V2 we have another two parameters. Here, so we define the ZNM in an n-port network, the Vn divided by In, then the other currents are 0. So here if I put I2 equal to 0, then the Z1 equals to V1 over. So this is how we calculate the values for the Z. So I just open circuit the port 2, no current is going inside that. I measure the voltage at port 1, and then I set that Z, okay, Z, for example, 1 is this way. Again, I open circuit the port 2, port 1, and then measure the V1, and then I set the Z1. Okay. The same thing we have for the admittance networks, admittance or Y matrix. So we say that the admittance parameters is the In divided by Vn, then the other V equals to 0. I mean when the other ports are get short circuit. So I short circuit port 2, so then V2 is equal to 0, and then measure the current at the port 1, and then I said it's okay, Y11 is this. It's clear. And we have these different representations because they are useful in different situations. We will see this. In different situations, for example, in one situation, the Z matrix is more comfortable, or ABCD matrix, or H matrix, or Y matrix. And then we define based on this. I mean, for a two-port network, I say that the voltage at port 1, how it depends on the parameters at port 2. Or the current at port 1, how it relates to the voltage and current. So ABCD matrix we define like this. And for the H matrix, actually we define the voltage 1 based on the current 1 and voltage 2. And the current 2 based on the current 1 and voltage 2. This is mainly used in the characterization of the transistors, low frequency model of the transistor. Remember that in low frequency we say that how we see that what's the HFE and then what's the H1. So these are what we learned from the analog electronic. Because output, for example, output voltage, it is dependent on the input current. So this is the relation. So an example of the networks, assume that we have this pi network. So this is the pi network. 1Z8, ZB, ZC, and I want to characterize this, and I don't want to consider that what's going on inside this. I just find the value for Z11, Z12, 21, and 22, and then we will have these values based on the definition, and then I have a Z matrix which is equal to this for parameters. Okay, and then I can say that okay, I don't know what's inside this, but it has a Z matrix with these values. For example, ZA parallel with ZB plus ZC or the rest. And this is what I just mentioned, that for example, a common emitter, a small signal model of a BJT transistor, we can draw the small signal model based on this, and then we can define the H parameters of that But what's the relation between the VBE and IB, which is the input impedance? What's the relation between VBE by VCE, which is the gain, or GM, and the gain of the transistor, and then what is the voltage gain, and then what is the relation between the IC and IB, which is the current gain, and then what's the relation between IC and VCE, which is the output, inverse of output impedance, and inverse of, this is the inverse of the forward gain, this is the inverse of output. Okay? Right. And is it? So I said that in which situations, which of them is more convenient. For example, if I want to put two networks in parallel, put them Z parameters is more convenient. Okay? So I have the Z parameters for network 1 and Z parameters for network 2, and then the Z parameters of the total is Z1 plus Z2. Okay. Then I want to make two networks in series. This is in series.
So each one is each one is
No, Z. We are
each one.
here. It's gone. So H11 was the input impedance of the H matrix of a network. H11 means for port 1. It's a definition. We say H11 and this H11. If you have your, I don't know why it's like this. Maybe the main problem is that this system is full. H11 is a definition here. So we said that H11 is the relation between the V1 and I1 if V2 is 0. I mean, if I short circuit the output, then what's the relation between the input voltage and current? I call it as transistor. Okay. Again, if we put the networks in series, but with this, I mean series of the inputs and parallels of the output, okay, then H parameters. So H of total is H1 plus H2, H prime plus H double. If we put the two networks in parallel and I want to find the network parameters, then the y parameters is, and then we can say that the y1 plus y2 shows the y of 2. This is why we go for the different representation of the network. And if we put two networks in cascade, so I have network 1, and this is very common in electric. For example, you have a network 1 and another network, and you want to connect these two together. So what will be the parameters for the whole? Then this is ABCD1 multiplied by ABCD2. So ABCD parameters is very useful. Most of the scientific papers, they have different components and they want to show that what's the whole performance of the circuit. They use ABCD matrix. And then here we have the ABCD parameters for single components. For example, for a single transmission line with the impedance of Z, then the ABCD matrix is this value. For a transmission line in parallel, then the ABCD matrix is this number, these numbers, and then for the T network, for a pi network, for a transmission line with the length of L, and then for a transform. So these are the ABCD values for the ABCD.
How are you going to use this?
You have this circuit, and then you have a transmission line, and you want to see that what's the whole thing. So you find the ABCD of the first one, you find the ABCD of the second one, and then multiply it together and say that okay, cascade of these two has this ABCD. And then all these parameters can convert to each other. For example, if you have the Z matrix, you can find the ABCD matrix. Or you have the Y matrix, you can find the H matrix. Or for two-port networks. We are talking about two-port networks because multi-port networks, we have only Z and Y. We don't have A, B, C, or H. Okay. This is an example. Okay. This is an example. We have matrix 1. We have network 1. So this is the network. This is our matching network. I have one transistor. This is the second network. The output matching network, third network, and then the feedback, which is the fourth network. So if I want to calculate what is the value for the whole network, I calculate Y. First, I calculate the H matrix for this. Then I convert the H to Y. So first, the H of the transistor, then I convert it to Y of the transistor. And then I add this Y to the Y of the resistor. Okay? And then I change all these two as the ABCD. Change it again to the ABCD of the combination of the transistor and resistor. Okay? So this is the ABCD of this part. And then I multiply the ABCD of the input network, multiply by this, and then multiply by ABCD of the last. This is how it works. This is why the networks are important, because maybe analyzing all these together is difficult, but analyzing every part is much easier, especially for the computer programs, because computer programs, the conversion of the matrices, these things are very easy, and you can do that there. Okay. In high frequency, but these are for low, mainly for low frequency. In high frequency, we are defining something else, and this is S parameters. So networks are mainly represented by their S parameters. And S parameters actually coming from the idea of the power, meaning that how much power we send to the one port then how much power we receive at the other ports, or the same. This is coming based on power, because in the high frequency we are always interested in power, how much power we generate, how much power we can transfer, how much power is reflected back, how much power is lost inside the network. So these are the things that we are, it's a matter of power. So I believe you, okay, we are defining two new parameters, AN and BN. And then I said that this AN equal to this equation. And you remember that from previous lecture, that if we want to calculate the power of this Pn, power of Pn, which is related on the voltage of network, voltage of 1 and current of 1, then this is the formula. And this formula is then simplified into this or this. And then we call this the power that we sending to the port 1, and this value is the power that reflecting back. So the average power as at any port is the power that we are sending and the power that reflecting back. So based on the definition of this Vn and In and this A. And because of that we said that we are interested in power, because you see that this An and Bn are in the form of power, mainly are in the form of power instead of voltage and current. And here we say that based on the formulas for Vn, that you know that Vn equals to Vn plus Vn minus the forward voltage and backward voltage, and In again equals to In plus In minus. Then if you replace these two, we find that An equals to this one, which is forward, and this one, which is back. Yeah. And then we define the S parameters as these values. I mean the reflected power, for example, we define the S11 as the reflected power divided by the incident. I mean how much power I send to the port 1, then how much power I received at port 1 when there is no power at port 2. What does it mean when there is no power at port 2? Because for the Z parameters, for example, I said that when there is no voltage. And for the Y parameter, I said that then, for the Z parameter, I said that there is no current. For Y parameter, I said there is no voltage. And I said that there is no power. What does it mean? Okay, I mean, what's the condition for no power? No power at port. I mean, no power coming to port 2. Short circuit. Match. Not mismatch, match. Yes, I mean no power is coming from port 2. If you match the port 2, nothing is coming back. So we have a two network, okay? I transmit a power A1 and then I measure something which comes back, okay? If I want to make sure that nothing is coming from this port, I just need to match this, okay? So for the Z network, we open the port because we said that no current is coming. For the Y network, we short circuit because we said that no voltage should be at port. And then we calculate the for example, y parameters of the port. For the s parameters, you match, and you want to make sure that there is no power coming from the other port. So this is port 1, and this is port 2. And then we define, for example, S21, how much power we receive at port 2 when we transmit something at port 1. And then we say that when the again the A2 equals 0, I mean no power is coming. If you match here, and then we measure what is coming. I mean nothing generated from port 2 into the network. When nothing is, when from these 2 points, nothing is going into the network. When we want something like that, it means that we have to match it. Because anything which comes out of this network, or anything which comes, for example, from the space, if you match here, it damps it. No power. No power. It could be a reflection, or it could be something which comes from something else. And then it could come from your network. Yes. It could be, the source could be internal or external.
Yes. What power is on the port 2, but not power.
S21 means the power which is received at port 2 and transmit from port 1. S11 means the power which is received at port 1 and transmit at port 1. How many power I transmit in port 1 and then I get that. It's kind of, the meaning is a reflection, which I mentioned. Okay. The same thing for the other port. How much power I received at port 1 when I transmit something at port 2. And the same thing for the S22, which is again the definition for the reflection coefficient right now. So based on these two, we see that the V1 divided by I1 is V1 minus plus divided by V plus minus. So you look at these two equations. So A1 is V1 plus divided by square root of Z0, and B1 is V minus divided by square root of Z0. Okay? So the B1 divided by A1 is this value, and you know from previous lecture that this is gamma, and this is gamma. Okay? So these two parameters are actually has a kind of tangible meaning for S11 and S22 are the reflection coefficients at the port 1 and port 2. And then you remember from the previous lecture that this is the formulas that we have for the power, and then we can say that the power that we received at port 1 is this value, and the power that we received at port 2 when we transmit at port 2 is this. Okay? You remember the equations and the definitions for the return loss and insertion loss. We had this last lecture, and then we see these two new definitions based on the S11 and S2. So the insertion loss is the how much power that we transmit from port 1 and we receive at port 2. I mean, how much power that we cannot receive. 1 minus that. And insertion loss, how much power that we transmit and it's reflected back. So the way that we measure the S parameters, we are using VNA, vector network analyzers, to measure the S parameters. So we have a transmitter and we call it RF. So we are transmitting a signal from here, and I want to measure the S parameters of this device, which is the device on the test. Okay. So I want to measure the S parameters of this, and then this device under test, for example, we bias it, we use this bias, we will see this later, what are these bias, and then we use two directional couplers. So directional couplers actually for devices that separate the incident and the forward and backward way. So they have two ports. When you send signal, then it directs some part of that to this port. When you send signal from this side, then it directs it to this port. So nothing, when you send signal, it does not go into this port. Some of them is going forward and some of them is coupled to the forward coupling port. And the same for backform. Okay, so we send the RF signal. So some part of that we get at port R as a reference. I want to see that how much power I send. This is the incident. This is R actually shows the A1. And then how much power reflected back from the device is going into the port 2. So the A is showing the B1. And then the signal is going through the device and then go through the other direction. So some part of that I capture at port B, and then this port B is the B2, all right? And then the rest is going and damping. This is how I said that matched the port. Nothing is coming back, okay? And then the S11 is this A divided by the reference that we got, and then the S21 is this B divided by B. This is how we measure the S11 and S21. And then if we want to measure the S12 and S22, then we need to just do this way around. I mean, rotate this, turn around this device under test, and but the current network analyzers has already two ports, and you can do it at the same time. Turn around but the device under test to do it for you. There are 2 ports or more than that for 4-port networks, for 8-port networks. We have very high performance DNA these days. Okay.